The final question we're going to ask about the squirrel, given its graph, is has the squirrel made it back to pole A by time t equals 8? So the real question is, has the squirrel made it back? What kind of question is that? That's asking about what? That's asking about position, right? And we want to know at time t equals 8. Well, remember, the graph gave us velocity, and we need to figure out position. So what does that tell you? It means we're going to have to find the area, right? Because if you're going from velocity to position, you're moving backwards. You have to find the area under the curve. So what we want to know is at time t equals 8, has the squirrel made it back to its original starting position? Again, here's the original preface of the problem. The squirrel starts at point A. It's trying to get to point B. Initially, its velocity is negative, so it's moving backwards. We just figured out in part C that at some point in time it starts moving to the right again. We just want to know at time t equals 8, has it actually made it back to where it started, right? That's all we're asking. So it moves to the left and starts moving to the right. At time t equals 8, has it made it back yet? Has it passed it? Is it over here somewhere, not quite back to point A? That's all we're asking about squirrel. Now remember, this is the velocity graph. So at time t equals 8, it's a positive 2 velocity, but that does not mean the squirrel is 2 feet to the right. This is not the position graph. So how do you find position? Well, that's where the area under the curve comes in, right? If you find the integral or the area under the curve of velocity, that will give you its change in position. And since it initially started at point A, and we know its initial position is 0, then we can actually just find the change in position from 0 to 8, and that will tell us whether or not it's to the right or left. And the way we do that is to find this area. If this area is positive, that means it has a positive position. If this area is negative, it means it's to the left of its starting position. It has a negative position. So I will go ahead and reiterate that with these steps, and let's figure it out together. Step 1, remember, is to interpret what is given verbally as a graphical expression, what I just went over. Time t equals 8, we need to figure out the squirrel's position at t equals 8. Graphically, this would mean the signed area under the curve. Now, I do want to underline that word signed area, because that means we have to count area under as negative and area above as positive. Remember, we're not talking about total distance traveled here. In that case, you'd make everything positive. We're just talking about its position, which is signed area, under the curve of v of t from time t equals 0 to time t equals 8. Now, I will say this. We want to go from t equals 0 to t equals 8 because we know its initial position is 0. If its initial position was given in the problem as something else, we would have to add the change in position, or the area under the curve, to the initial position to get its final position. But in this case, its initial position is at point A, so we don't have to do that. But just remember that, because sometimes that happens. Okay. Step 2 is to interpret the verbally stated question as a graphical expression. Has the squirrel made it back to pole A by time t equals 8? This would mean that the squirrel's position would be either 0 or positive. So its position has to be 0 or positive for it to make it back. Algebraically, S of t is bigger than 0. The graphical interpretation of this would mean that the signed area under the curve of v of t, which gives you the integral of velocity, which is position, at time t would have to be either 0 or positive. It's unclear as to when this actually first occurs. The math for that is absolutely mind-boggling and requires conic section equations. Okay, that is true. We could actually, though, kind of eyeball it. Made this lesson several years ago, but you can eyeball it, actually. You can tell that, for example, at time t equals 4, the only thing that this positive area is going to cancel out right here is this area right here. I'll even shade it, okay? So this area will cancel this area, but it won't cancel this area out, right? It actually really doesn't look like it cancels out until somewhere around the time we're looking at, because basically what's going to happen is, let's use this green. No, let's not use green. Let's use purple. This area right here, these areas look like they might almost cancel this area out to the point where it might be back where it started. So we can guess that somewhere around t equals 8, these areas cancel and its position is back at point A of the electric line. But that's why we're doing this problem. It's an interesting problem because it's a pretty close call. Step 3, consider the appropriate motion relationship chart. We are integrating velocity to get to position, so the integral of velocity equals S of t in this case because we're going from here, we're having to do A and B here. What it actually gives you is S of B minus S of A, which is displacement. But again, in this case, since initial position is 0, its displacement is its position. Okay, so that being said, we're going to solve the problem using the graph, the area under the curve, or the slope. In this case, we're going to be using the area under the curve. The area under the curve of this graph at time t gives you the position of the squirrel at time t relative to pole A. This comes from what? The fundamental theorem of calculus. The first area from time t equals 0 to time t equals 2 is given by a triangle. So we're going to look at this down here. Now this triangle, we're going to draw this triangle in purple right here. Okay, and we'll box it off right here. Can everybody see that this triangle is actually half of this square? And this square is 2 by 2, so it's 4, right? Well, half of the square would be this triangle, which is 2, and since it's below the t-axis, it's -2. That's the simplest way to do that problem. Okay. Now the next two areas cancel each other out. I'm going to put this in orange here. Okay, they cancel each other out because of the same triangle, one above, one below. So I'm going to call that area 2 and area 3. They equal 0. Now, area 4 is a little bit more complicated. This is area 4. It's all above the t-axis except for at t equals 6. How do we come up with this number? Now, if you can see this, everybody see that there is a rectangle right here with area 4 by 2, which is 8. So that's where the 8 comes from. And furthermore, this right here is a semicircle. If I take the area of the square and subtract the semicircle, I will get this blue area, which is what I'm looking at. To find the area of a semicircle, you need to know its radius. In this case, it's 2. And you just find the area of what the bigger circle would be and cut that in half. So pi r squared over 2. So that's basically how we get this. Pi r squared would be 4 pi, right? Yeah, pi times 2 squared is 4 pi. Half of that is 2 pi, which is the area of the semicircle. So if you take the area of the rectangle and subtract the area of the semicircle, you get what's left over, which is this blue area. So that's the easiest graphical representation. I've got some explanations there. You can read through all this technical writing if you want, but the rest of the areas, although not relevant now, will be used later on. The next, from t equals 8 to t equals 10, is a rectangle with area length times width. Next, from t equals 10 to t equals 11 is a triangle. Finally, from t equals 11 to t equals 12 is also a triangle. Let's figure out the net area of these shapes and place them on the graph. So we just want to figure out these, 4 areas that we just calculated. And basically, we're just going to add these areas up to get what the squirrel's position is at time t equals 8. So if we find that area, let's use brown. So S of t is equal to what? That's what we're trying to find. And we will find that by adding up these areas. So just add up all those areas. We said the 2 and that one right there is going to cancel. We end up with 8 plus -2, which is 6 minus 2 pi, which is -2.8. Whoops. Its position is what? Its position is negative, meaning it hasn't quite reached its initial position just yet. Okay? And so we can answer that finally. The squirrel has still not made it back to pole A at time t equals 8 because the signed area under the graph of v of t is negative from t equals 0 to t equals 8, he better book it. We should also note because s of 0 equals 0, right? Again, if the initial position was something else, we'd have to add the displacement to that initial position. Okay, so that's it for this question. The squirrel has not quite made it back to its starting point. Going back to the initial, what I initially drew here for this problem, basically the squirrel is somewhere around here. It hasn't quite made it back to point 8 yet. Looks like just after time t equals 8, somewhere like 8.3 maybe is when it finally reaches point A again. If you have any other questions about this problem with the squirrel reaching its initial position, let me know.